Here in Atlanta, we are home to the world's busiest airport. They have 5 runways and 2,500 arrivals and departures per day.
Have you ever wondered how they schedule all those flights? Those runways are putting out a plane every 30 seconds.
Wow. It turns out this is an example of a classic AI problem called constraint satisfaction. Let's start out with a simple example as a challenge question. Map coloring is another classic example of constraint satisfaction.
We are trying to color this map of Australia using the minimum number of colors possible, but making sure that no neighboring regions have the same color.
I guess if they had the same color, it would be hard to tell where one territory stopped and where the next began.
Exactly. We can set up the problem more formally by first listing all the variables. In this case, the territories.
And the possible colors for the territories are listed as the domains of the problem.
Finally, the rules of the problem, that no territory can be assigned the same color as a neighboring territory, are listed as the constraints.
We can do that explicitly by listing all the possible pairwise constraints, like how Western Australia's color can't be the same as the Northern Territory. Or we could list all the allowable assignments for each pair of territories.
A solution is an assignment of colors to each of the territories that satisfies all the constraints.
I always wanted to paint Australia red. Anyway, unary constraints restrict the value of a given variable, like saying Tasmania can't be purple.
Binary constraints relate at most 2 variables. We can represent those with a constraint graph.
Here's a constraint graph for our Australia coloring problem. Nodes are the variables, like Western Australia, South Australia, Queensland, etc. Arcs show the constraints between the variables.
We can apply general-purpose constraint satisfaction problem algorithms to the graph structure to speed up our search for an answer. For example, Tasmania is independent from the rest of the problem. Now try this map coloring problem. Color each region by typing in a number to represent your color. For example, type the number 1 to represent color number 1, 2 for color number 2, and so on. What is the minimum number of colors needed for this map? Here's one possible set of answers. Answers could vary depending on where you started coloring in the map. We need 4 colors at minimum to color in this map because of all the adjacent regions in the center.
Besides unary and binary constraints, we could have constraints that involve 3 or more variables, or soft constraints, like the fact that I prefer to teach on a Tuesday-Thursday schedule. Problems with preference constraints are called constraint optimization problems, and are solved with linear programming.
There are lots of examples of constraint satisfaction problems. Sudoku is a classic game which can be solved with any of the methods we will be teaching.
Other examples include car assembly, job scheduling in factories, class scheduling, spreadsheets, transportation scheduling, or floor planning. Many of these require real-valued variables.
So which algorithm are we going to show first to solve constraint satisfaction problems?
Well, the stupid one first, of course.
I had to ask.
Then we'll add intelligence as we need it.
Okay, we'll use simple search. States are defined by the values assigned so far.
The initial state is the empty assignment. First, we'll check to see if the current assignment is the goal.
Then we will assign a value to an unassigned variable that does not conflict with the current assignment.
We call it a dead end if there are no legal assignments. In that case, we will back up to the previous state and try another assignment.
And we recurse until you either find the answer or try all the possible assignments and report failure.
Let's make the algorithm concrete by doing an example.
Okay, here's our map of Australia.
We will work with Western Australia first. It can have one of 3 colors, orange, green, or blue.
I'll choose orange.
Okay, what section do you want us to look at next?
How about the Northern Territory?
Great. Since we chose orange for Western Australia, the Northern Territory can have 2 colors, green or blue.
Let's choose green.
Okay, now let's work with Queensland next. It can be orange or blue.
Let's choose blue.
But now we are in trouble. There are no colors left for South Australia.
Okay, well, that's a dead end. Let's back up and try the other branch where we only used orange and green up to this point.
And eventually we'll find the answer this way, but we can improve the efficiency of the algorithm significantly.
I guess we've already seen one optimization.
How so?
Well, if I choose the least constraining value for Queensland, we would not have had to back up. Let me show you. We started with Western Australia being orange. Then the Northern Territory was green. Since Queensland is not next to Western Australia, I can use orange again. That will leave blue unused.
Okay, so orange was the value that least constrained our future choices.
Now you get it.
Another optimization is to choose to assign the variable with the minimum remaining values next.
If we start with assigning Western Australia and then the Northern Territory colors, the variable with the least number of values remaining is South Australia, so we should choose that one next to assign.
What if I have a tie?
What do you mean?
In this example, we have assigned Southern Australia and Northern Territory. There are two regions that can be only assigned orange, Queensland and Western Australia. Which do we choose?
Choose the one with the most constraints.
Ah, you mean Queensland in this case, because it borders New South Wales, as well as the Northern Territory and Southern Australia. Western Australia only borders Northern Territory and Southern Australia, so it's not as complex. By choosing the one that's more constrained in the future, we'll be able to run into problems sooner rather than delaying them.
Correct.
Okay, well, how much do these improvements to backtracking help?
Remember our n-queens problem?
Yeah.
Well, it is another example of a constraint satisfaction problem.
Okay.
And using the least constraining value and minimum remaining values heuristics to improve backtracking search will allow us to do the 1000 queens problem.
I don't think I could ever do that by hand. That's impressive.
You haven't seen anything yet. Let's consider the optimizations we just discussed. For this half-colored map, which region should be filled in next in order to minimize backtracking? There might be multiple answers here, but choose one of these optimizations, and choose the region that matches with that. Here are two possible answers. This region is bordering a green region and an orange region, so it only has two options for colors. Compared to all our other regions, this has the minimum remaining values of those regions. For this region, we can pick the least constraining value, which is green in this case, because its bordering region can only take light blue or dark blue, so avoiding those two choices gives us more options later on. Our next optimization is forward checking. Basically, for each unassigned variable, we are going to keep track of the remaining legal values.
I get it. So if we ever make a decision that causes an unassigned variable to not be able to have a value, we stop our search and back up.
Right.
Let's try that with the Australia example. We start with nothing colored, and all the regions could have any of the three colors.
In our first step, we assign orange to Western Australia. That removes orange from the colors available to the Northern Territory and to Southern Australia.
Suppose we assign green to Queensland. Now, both the Northern Territory and Southern Australia can only have blue, and New South Wales can have orange or blue. If we assign blue to Victoria,
then we see that New South Wales can only have orange, the Northern Territory can only have blue, and South Australia can't have anything.
So we figure out that we are stuck and can backtrack earlier than we would have if we tried to continue assigning variables.
Exactly. Forward checking is an early warning system that a search is going down the wrong branch.
However, I noticed we could have stopped our search earlier.
How?
At this step, we said the Northern Territory and South Australia both had to be blue.
So?
But these two regions are adjacent. We know they can't both be blue.
I see. Forward checking propagates information from assigned to unassigned variables, but doesn't provide early detection for all failures. Instead, we can use constraint propagation repeatedly to enforce all the local constraints.
We can use arc consistency for a simple version of constraint propagation. A variable in a constraint satisfaction problem is arc consistent with respect to another variable if there is some value still available for the second variable after we assign a value to the first variable. If all variables in the graph satisfy this condition, then the network is arc consistent.
Let's look at a practical example. Once we get to the stage of assigning green to Queensland, we look at all of its neighbors that are unassigned and see if the assignment of green reduces the number of colors available to them. If so, we remove that color from the neighboring region, and then look at its neighboring regions to see if we need to propagate the change onward. We keep doing this process until it terminates, or we determine that one of the regions does not have any colors left.
So here we have removed green from South Australia's list and are now looking at its neighbors. New South Wales is a neighbor, and in order to be arc consistent, we will have to remove blue from its available colors. It can only be orange.
Victoria is a neighbor of New South Wales, so we look to see if the change affects it. In fact, it does. We remove orange from Victoria's list of available colors. Our choice of green for Queensland has caused a chain of changes in possible values for our variables.
Why don't we remove blue while we're at it so Victoria doesn't conflict with South Australia?
Well, we haven't gotten that far in our queue of things to check yet. Next, we're going to look at the Northern Territory because it is another neighbor that might be affected by South Australia's change. In fact, we see South Australia and the Northern Territory are both restricted to blue, which is not allowed, so we return a failure and force the search to try another option for Queensland.
Wow, that was a lot of work.
But it can save a lot of unnecessary deep searching for more complicated problems. Here's a map where we've colored in two regions for you. So given this state in the map coloring, propagate through the constraints to make each variable arc consistent. Check the boxes to indicate which color is possible in each region. Finally, is the entire network arc-consistent? Here's the answer. We have several islands in this map, so they can have any of the three colors. However, K2 is constrained to only one color, green, because of the two bordering regions. Finally, the entire network is arc-consistent because we don't have any regions without a possible color.
Speaking about saving time through deep searching, another powerful trick is to look at the structure of the problem and see if we can decompose it to several independent problems.
For example, Tasmania is independent of the rest of the Australia problem. We can solve it separately.
Which takes a level off our search tree. In general, suppose we have a problem with 80 binary variables. We can divide it into 4 problems of 20 variables. We go from a search space of 2 to the 80th to 4 times 2 to the 20th.
Even better, if we have a CSP where there are no loops, we can solve the problem in OND squared time instead of OD to the n.
How?
We pick any variable to be the root of the tree, and choose an ordering of the variables such that each variable appears after its parent in the tree. We then start at the end and make each parent arc-consistent, going up the tree until we get to the top.
What if that is not possible?
Then we report failure of the problem.
Okay, what's next?
It's simple. We start at the top of the tree and pick any assignment available, going back down the tree until we get to the end. Since the tree is arc-consistent, any of the available assignments will solve the problem.
How fast is this process?
O of nd squared, where n is the number of variables again, and d is the size of the domain.
So this trick really helps out with the speed of finding a solution. But what if the constraint graph really isn't a tree?
Well, sometimes you can condition a problem by assigning values to subvariables and change a constraint graph into a tree.
Huh. Like with our Australia coloring example. If we assign a value to South Australia first, and remove that value from the possibilities of its neighbors, then the problem becomes a tree, and we can use our fast method to solve the problem.
Precisely.
Hold on. We said that n-queens was a constraint satisfaction problem, but we covered that in the last lesson using genetic algorithms or hill climbing algorithms to solve the problem.
That's right. We can randomly assign values to the variables and iteratively improve the assignments until we come to the solution.
Like our previous example with 4 queens, while there were 4 to the 4, which equals 256 possible states, we can quickly find the solution by minimizing the number of attacks with each improvement.
In fact, this minimizing conflict method can solve n queens with n equals 10 million. In the million queens case, this min conflicts algorithm can solve the problem in an average of 50 moves.
Wow. I guess that's because there is a large number of solutions to the problem.
Yep. Iterative improvement algorithms work well when there are many solutions and when there are very few. However, there are problems where the number of constraints versus the number of variables hit a certain ratio, and the problem becomes very hard to solve.
Well, then let's stick to the easy ones.